Hi, I'm Andreza Ahmadi, and I'm going to talk about how to autonomously guide a robotic agent using visual navigation in arable fields. Autonomous navigation of a robot in agricultural fields is essential for everyday tasks, from cultivation, crop monitoring, and weeding. Many current approaches rely on accurate GPS, however, such technology is expensive and can be impacted by lack of coverage. As such, autonomous navigation through sensors that can interpret the environment, such as cameras, is important to achieve the global autonomy in agriculture. In a prior work, we have introduced a navigation scheme which could successfully guide a robotic agent throughout single lines of crops. However, this approach was not considering the real open field challenges like different crop types, illumination variation, appearance of weeds, and uneven distribution of plants in the rows. So here we propose a real field applicable method to automatically detect the number of crop rows and reliably guide the agent throughout the lanes of crops, and at the end of the lane, switch to the adjacent lane autonomously and without any human intervention. Here in this representation you can see different steps required for our navigation scheme that includes identifying the number of crop rows underneath the robot and then guiding it throughout the lane using the front camera, and at the end of the row it will switch to the back camera to exit the row, and then by side movement it will look for the next lane to follow. To locate the crop rows underneath the robot, we first need to locate the crop rows underneath the robot by extracting the crop centers within the rows. For this purpose, we first extract the vegetation mask using classical machine learning algorithms, which can give us the results as you see here without any hyperparameter tuning. One issue associated with this technique occurs when multiple plants are absorbed into a single large region, most often occurring with bushy plants, as you can see in the right side. To reconcile this, we divide the contours into smaller subsections if they exceed a predefined maximum height, which can avoid from the further problems in locating the crop rows. After extracting the crop centers visible in the field of view of the camera, we locate each single crop row using a novel moving variance technique, which can reliably detect the crop rows regardless of plants' phenotypic characteristics. As the sample outputs of this technique represent, it is able to extract the crop row lines of 5 different crop types with different growth stages and canopy types. We evaluated the performance of our proposed approach also in a gazebo simulation environment with different configurations of crop rows, also with appearance of the weeds, which the results showed the validity of our approach. Ultimately, after localizing the crop rows, we guide the robot throughout the crop rows using a visual surveying controller, which the lines and their intersection point with the bottom of the image are the features which are fed to the visual surveying controller for generating the velocities of the robot. Here a simple scheme of the proposed control loop is shown where the S star denotes to the desired feature, which is the vertical center line in the image, and the IVBS controller will generate proper velocities based on the extracted features from current set of images taken from the cameras. Here a sample output is represented. As you can see, the approach is able to guide the robot throughout 2 different crop rows, required minimal hyperparameter tuning. Also here the footage of the robot while navigating through the 3rd crop, which is the sugar beet, is shown, and you can see that navigation approach can handle different challenges of real world and guide the robot throughout the lane. In the navigation scheme, when the robot reaches to the end of a lane, it will use the back camera to exit the row, and after exiting the row, it will stop, obtain distance from the crop rows, and then by a side movement, it will try to recognize and count the new crop rows entering the field of view of the camera. With this approach, it can locate the new lane and start following it to the end. For implementing the recognition part, we use similarity distance between the stiff features of the vegetation indexes of crop rows. In this example, you can see a complete traverse of the robot from the lane which it was following to the next one, and then starting to following it back to the end. This example has been recorded in the crop rows of beans, which due to appearance of weeds, uneven start of crop rows, and a special shape of canopy type, it provided a pretty challenging environment for testing visual navigation. By this, I want to thank you for your attention and invite you to visit the repositories of both versions of this project.